Hey yo, bro, I think my girl's lying to me. I'm gonna end it with her.
Oh, really? What's she lying about?
Well, she said she was going to Tesco innit? There's only 1 mile to get there. I tracked her phone, said she travelled 2.2 miles. She's definitely cheating on me.
Whoa. Firstly, why are you tracking your girl's phone? That's very controlling behavior. Secondly, what you measured was the displacement from here to Tesco. That's a straight line distance. The route your girl took probably wasn't a straight line, so the actual distance was longer. Don't worry, she didn't cheat on you today.
Aye, my bad. Wait, what do you mean not today?
So today we're going to talk about differences between scalars and vectors. Now you may have come across this before, so the definition for a scalar is something that only has magnitude. And what that means, it has some numerical value, and that's just it. It just has a number. Vectors are something that have both magnitude and direction. So this can be a number followed by an angle, maybe a positive and a negative sign, something like that. Some examples of scalars, we can say time, distance, mass, speed. These are all scalars. These have only a number. So your time can be a certain number of seconds, distance a specific length, mass is just your mass in kilograms, your speed is just a number. Some vectors, for example, could be velocity. Velocity is the vector version of speed. It's the magnitude of a speed in a particular direction. And you can also say the same for distance. The displacement is sort of the vector version of distance. It is the straight line distance between 2 points. Whereas the distance, if you let's say we were going between A and B, you took this random path here. To measure along this exact path how far that is would be measuring the distance. But this distance straight from A to B is your displacement, because you're measuring it in that particular direction only. Some other examples of vectors can be force, acceleration, and moments. So let's say you were given a vector diagram, for let's say a force diagram, and you were asked to resolve these forces or resolve the vectors. Now it's not really common for you to resolve it through diagrams and scalings, but it might be a worthwhile skill to learn. Now if you were asked to find the resultant force, the more typical way would be to solve it using calculations and equating horizontal and vertical components, which we will go through later on today. But another way to do it is also by drawing a force diagram, and sometimes it may ask you to do this in the exams explicitly. So how would you do it? Well, first of all, you pick a direction. And you pick your first force. So let's say I'm going to start with this 6 Newton force, and I'm going to work around all the forces in the anti-clockwise direction. So let's start by drawing the 6 Newton force. And the things you have to make sure is you have to draw everything to scale. I can't really draw it to scale here, I don't really have a ruler. But when you're doing it, you make sure you're always using a ruler and using a scale. So let's say in this case, you could use a scale of 1 centimeter for 2 newtons. So I'll draw a 3 centimeter line here to represent that 6 Newton force. And the next force that comes along is this 10 Newton one, and that's directly upwards. So that will be of length 5 centimeters. And then you also have the 20 Newton one is the next one, so you're going around this direction, 20 newtons, and that's going to be 10 centimeters. That'll probably go all the way along there somewhere, 10 centimeters. And your last one is this 12 Newton force, in which case you have to get out your protractor, find the line at which it's 30 degrees, and you draw a 6 centimeter line to represent the 12 Newton force. And then you have your 2 points, your start point here and end there. And you simply connect it up with a line. You want to measure the distance or the length of that line. Now, the more typical way to resolve vectors is by using angles and calculations. So, let's say I had a plane surface here and a plane surface there. So let's call this our vertical axis and horizontal axis. Let's say I'm applying some force of, say, x newtons at an angle of theta to the horizontal axis. Now, the typical way to resolve vector diagrams is by taking components with respect to the horizontal and vertical axis. So what you're basically doing is you're rotating this force through this angle and projecting it onto this axis here. So you can see we'll have a length of there. And you'll do the same for the vertical axis. And you want to find out what is that length and what is that length. And here's the trick. Whenever you move through an angle, you use cos of theta, given that theta is your angle. So in this case, if I'm moving towards a horizontal axis, you can see I'm moving through that angle. I'm moving through this angle, down where the angle is. So in this case, the horizontal component is x cos theta. Now, if I wanted to find the vertical axis, you can see that I'm moving away from the angle. You can see that the angle is marked here. I'm moving away from it. So away from the angle, you use sine theta. So the vertical projection, or the vertical length of this component is x sine theta. Now, how do we know this works? Well, you know Pythagoras' theorem. You know that the bottom length is x cos theta, and the vertical length is x sine theta. We know that the actual length of the force is x newtons, so you can say that, due to Pythagoras' theorem, x cos theta squared plus x sine theta squared should give you the length of that original force. And if you do this, you'll get x squared cos squared theta plus x squared sine squared theta. So you can factorize out an x squared, and you get cos squared theta plus sine squared theta. And if you're doing A-level maths, or if you've come across this maths term before, you will know that cos squared theta plus sine squared theta is 1. So this is just equal to x squared. And that makes sense because that is what the length of the hypotenuse in this case is squared. So let's look at an example where you may need to resolve forces, and resolving a lot of vectors and stuff, resolving a lot of forces will be quite useful and come up a lot whenever you're doing questions based on moments, which we will cover in a later video. Let's say you had this surface that is inclined at an angle of 30 degrees. Okay, and you have this block, let's say 10 kilos, 10 kilogram block just resting on the surface. I'm going to name one force acting on this block, and that force is its weight. The weight of this block will act vertically downwards, right through the center of the block, acting vertically downwards towards technically the center of the Earth. And we know that weight is equal to mass times gravity, and that's equal to, well, the mass is 10 kilograms times 9.81, which is the gravitational field strength. So I'm going to call it 10g. And in this case, remember that g is the gravitational field strength, is not grams. A lot of times it'll be very comfortable for you to carry around g throughout your equation instead of always putting in 9.81, 9.81. And sometimes your answer is required to be left in terms of g. So it's a good practice to not sub in the value of g immediately and to carry it around with you in equations. So if I said I want to resolve components parallel and perpendicular to the plane. So here you'll need a bit of trigonometry. So you know that these two, you can kind of see that they meet a right angle. And that's true because this is horizontal to the surface and the weight acts perpendicular to the surface. So you know that this is a right angle. And you know because of triangle rules, this will be 60 degrees. Now if I were to draw a perpendicular line to the surface, it would look something like this. So if I wanted to work out this angle, we know that because it's perpendicular, this whole angle here is 90 degrees. So this angle here is 30. And you can see that this angle here is equal to that angle there. And knowing that fact will prove very, very useful in certain cases, especially in moments. So if you can notice a situation like this, it's always nice and quick and simple to just label these two angles immediately. If that angle is given, label that one, especially in moments, because you're almost always going to be using this angle. And I want to find the components of the weight parallel to and perpendicular to the slope. So firstly, if I were to go through this angle, we can see that there's a component of this weight along this line. And you know I'm moving through the angle. So in this case, this component is equal to W cos 30. So the component of weight perpendicular to the slope is equal to 10g cos 30, where 10g is your W. And if I want to find out the component parallel to the slope, I move away from the angle onto a projection about here. And because I'm moving away from the angle, I use W sine 30, which is equal to 10g sine 30. I advise you to go look at some practice questions in order to help reinforce what you've learned today. It's a good way to understand how to apply the content and the equations. Please make sure to subscribe, like and comment, and feel free to watch any of my other videos if that will help you with your physics course, and good luck for your future.